This is a fossil of a relative of Ankylosaurus in the genus Boreopelta markmitchelli, and this fossil is special because it has preserved skin impressions from when it was alive. What is really exciting about those skin impressions is that they suggest that dinosaurs might have had a superpower. Hi and welcome to Paleo Logic at Esme, and today we're going to talk about a potential new discovery about how dinosaurs maintained their body temperature. Okay, so why is this particular fossil such a big deal? Well, these types of fossils are rare. Preserved skin impressions from dinosaurs are rare. And there's a bunch of different reasons for that. Like, for one thing, skin doesn't preserve very often. It either decays before it can become part of the fossil record, or if it does preserve, it usually just becomes like a thin film of carbon and it doesn't have any three-dimensional structure left. So what we're looking at here is actually pretty exceptional. But beyond that, what makes this particular fossil really interesting is that the preserved skin impressions are of structures called integumentary, and these are little plates of bone that were embedded in the skin of some dinosaurs and other reptiles. They're not armor, although sometimes people call them armor, but the function of these bones is still kind of an open question. There have been a lot of ideas out there. Some researchers think that they helped with Some researchers think that they might have been involved in display or attracting mates. Some researchers think that maybe they provided protection against predators, or that they were sensory organs. So there is a lot of ideas out there, and that is one of the things that makes them so interesting. We don't know what they did. Now, to be clear, these structures are different from the scutes that are found on turtles. So these are little plates that are made by the dermal tissue, and then also they're made of bone. They're different from the scutes of turtles, which are made of keratin, which is the same stuff your fingernails are made of. So it is cool to see this structure preserved because it is something that we would never see in a fossil otherwise. It would just look like a carbon film on the outside of the dinosaur. And that's not super Seeing these actual bony structures gives us a better idea of what was going on. And specifically with this fossil, what's interesting is that we can actually see vascularization of the skin, so we can see blood vessels that went through these structures. And that tells us that these structures were probably metabolically active. And if they were metabolically active, they were probably doing something to help the animal regulate its temperature. And this isn't just true for dinosaurs. This is true for all kinds of animals that have these structures. But in dinosaurs, these structures seem to get really big. And that's also another piece of evidence that they were probably involved in So these structures evolved independently multiple times in dinosaurs. So that suggests that there was some selective pressure favoring them. So this paper is arguing that the reason dinosaurs got so big is because they were able to use these structures to radiate heat. And that's something that mammals do today. We radiate heat to keep ourselves cool. And sometimes that process requires blood vessels close to the surface of our skin. And that's exactly what we're seeing in this fossil. If this hypothesis is correct, it would mean that dinosaurs could turn up the heat or turn down the heat depending on what their internal temperature was. So they would have had a type of thermoregulation similar to what we see in mammals and birds today. And that would make dinosaurs a type of what's known as a warm-blooded animal. Now, there are different types of warm-blooded animals. There's poikilothermic, which means that their temperatures vary and they rely on external sources of heat, like a lot of reptiles do today. Then there's homeothermic, which means that they maintain a stable internal temperature no matter what the environment is. Birds and mammals are The problem with the idea that dinosaurs were warm-blooded is that it is generally thought that the evolution of warm-bloodedness happened only once so it happened in the lineage leading to birds and mammals. And since dinosaurs are more closely related to crocodiles and turtles than they are to birds and mammals, it seems unlikely that they would have evolved warm-bloodedness independently. That means that if dinosaurs were warm-blooded, they probably inherited that trait from their ancestors, and that ancestor would have had to have been warm-blooded itself. So the inference would be that warm-bloodedness evolved more than once Now, it's also possible that dinosaurs didn't inherit warm-bloodedness from their ancestors, but instead evolved it independently. So this new paper is suggesting that dinosaurs were warm-blooded, but they weren't homeothermic. Instead, they were so they couldn't maintain a constant body temperature, but they could change their temperatures, and this fits with the fact that we find dinosaurs in all different environments around the world. If they were homeothermic, we would expect to find them mostly in mid-latitudes where it's warm enough for them to survive. But since they were poikilothermic, they could survive in colder environments, so they could move into higher latitudes. That could explain why we find them basically everywhere. But there are other hypotheses for why we find dinosaurs everywhere. So this isn't like the only proposed explanation for that. Now, I should say that this paper is saying that dinosaurs were warm-blooded and that's why they became so successful. There are other papers that make that argument. But this paper is talking about a potential new piece of the puzzle, which is this idea that maybe dinosaurs used these structures to be poikilothermic to control their body temperature. I think this is an exciting line of research because it helps us understand dinosaurs better. It also helps us understand the evolution of birds. So traditionally it's been thought that birds evolved from small theropod dinosaurs, but it's not totally clear why those small theropods became birds and not something else. One hypothesis is that they started becoming warm-blooded and that gave them an advantage. Maybe that's what allowed them to take over ecological niches that were previously unavailable to dinosaurs. I also think it is worth pointing out that just because dinosaurs potentially had this type of thermoregulation doesn't mean that all dinosaurs were the same. Maybe sauropods were warm-blooded and ornithopods were cold. So even within the same group of animals, there could have been variation in how they regulated their temperature. Finally, I should point out that not everyone agrees that dinosaurs were warm. Some researchers think that dinosaurs were just kind of like today's reptiles, that they were basically cold-blooded and relied on the sun to warm them up. In favor of this idea, there's evidence that dinosaurs didn't shiver. Shivering is a way to generate heat internally, but we don't see evidence of shivering in dinosaurs. And if they didn't shiver, it's hard to imagine how they could be warm. Now, this fossil is of a relative of Ankylosaurus, and the author of this paper argues that dinosaurs and relatives of dinosaurs were probably warm, but that other types of reptiles like crocodilians were not. So it looks like this story will continue to develop as more evidence comes in. Thank you to my supporters for making it possible for me to bring you these videos. Special thanks to my top-tier supporters, and thank you all for watching. See you next time.